All right, welcome back to operating systems. Yeah, the exam content's exactly the same for 353. So, here is the first session for final exam review. So, I told Satao to start grading Lab 6 too, so if you have finished it already, then you can get your grade for it and you don't have to worry about it. So you can know your grade ahead of time. So he is periodically marking it, so pay attention to announcements. So, any questions? We're here for review. Anything in particular you want me to go over? Otherwise, we'll just randomly go over exams and you can stop me. Yeah? All right. So let's randomly start at, let's see. So here is the last semester 353 exam. 353, exactly the same course as your one, it just lasted for a week longer. So here is the final exam, so let's breeze through it and see what we want to do. So looking at the topics here, is there any topic we're particularly interested in? Locking. We all like locking? The hardest part? All right. Votes for locking. All right. So, locking. Consider the following code snippet. So we can see that. So we have 3 threads. Thread 1 that grabs mutex 1, and then mutex 2, and then thread 2 that grabs mutex 2, then mutex 3. And then thread 3 that grabs mutex 3, then mutex 1. So the question says, assume we only have 3 threads. We create 3 independent mutexes, so all mutex 1, mutex 2, mutex 3 are all initialized for us. And each thread executes its own different function above. So thread 1 executes thread 1, thread 2 executes thread 2, thread 3 executes thread 3. So, any questions with what's given there? So, let's see what the first question is. Identify and explain the deadlock condition that can occur in this program. So I was nice and told you that there is a deadlock. So can anyone explain what a deadlock condition is here? Yeah, so each thread just grabs the first mutex and then we get context switched. So in that case, let's see if I can write better. Thread 1 would lock M1. Thread 2 would lock M2, and then thread 3 would lock M3. Whoops, not M2, M3. Now, in this case, if every thread just grabbed the first lock, well, can thread 1 make any progress right now? No, because thread 1, it's going to try to acquire mutex 2, which is currently held by thread 2, so it can't make any progress. Thread 2 is going to acquire mutex 3, which is currently held by thread 3, so it can't make any progress. And then thread 3 is going to acquire mutex, or try to acquire mutex 1, which it can't because it's held by thread 1. So no threads can make progress in this scenario, therefore we have a deadlock. Questions, comments, concerns about that? Seems like a deadlock to me. All right, so 4 points to explain that. So that is the correct explanation. 6 points. Propose a solution to avoid deadlock in this code Modify the code or describe your proposed solution and briefly explain how it addresses the identified deadlock condition. So, how would we fix this deadlock? Yep.
Could we use try lock instead of lock in the second statement?
In the second statement for all of them. So just try. What else do we need to do in the try? Yeah, try in a while, and in the while loop we would have to do that unlock, yield, lock thing, right? Yeah, so in this case, if we try to get M2, then we would, if we fail, we would unlock M1, yield or something. Whoops, I don't know. I can write C, not English. So lock M1, and then we could have that in a while loop, and we could have that in every thread. So we get rid of, anyone remember what that condition for deadlocking is called? Hold and wait, yes. So that eliminates hold and wait because while I'm holding a mutex, if I don't get it, I give up the one I was holding. So I do not have that deadlock condition. So that is one. Is there another solution to this that only requires me to swap 2 lines around? Yeah.
For like the third thread, can you just like swap the mutex 1 and 3?
Yeah, just swap these two, like that. All right, if I swap those 2 lines, so instead of locking 3 and then locking 1, what if instead I locked M1 and then locked M3? Do I have a deadlock in that case? No. Why do I not have a deadlock in that case?
Thread 1 holds a lock, so thread 3 could not proceed to not get a lock.
Sorry?
So if the thread 1 holds a lock, so the thread 3 could not get the M1 lock.
Yeah, if thread 1 got the M1 lock, then thread 3 wouldn't be able to acquire lock 3 without also holding lock 1. So remember what that's called? That we broke in this case? Sorry? So thread 1, whoops. Let's see if we can come up with a name for this. So thread 1 in the deadlock condition was waiting on thread 2. Then thread 2 was waiting on thread 3, and then thread 3 was waiting on thread 1. Can we come up with a clever name for that? Not a race condition. Circular wait. So circular wait was another condition for deadlocking where I don't acquire the threads in the same order. If I acquire the threads in the same order in all of my threads, then I have a set order and I do not have a deadlock because I will not have a circular wait. So that is also a valid answer, is just to always acquire them in the same order. So you could get 6 points real quick if you just swap 2 lines and you explained it. All right. See, locking's not that bad. That was like what? Okay, it looks like 18 minutes. Okay, maybe it's not that bad. All right, yep. Yep, full marks for the try one. It's just a lot more writing, but it's fine. Still a valid solution. Okay, do we want to do semaphores? Okay, so let's see if I can make this better. No. Okay, I'll use you to cover up some answers. Okay, that didn't work. Come on. All right, that's scuffed. All right, so it says consider, That looks, okay, whatever. So it says consider the following code. We have a define that says total threads is 8. We have a center that we can initialize, and then a run. We have this initialize everything function, and the comment says we want only thread 0 to execute this, and that green line was not there originally, but you would have to have an if condition there, so I'll just give it to you. And then here it says we want all cores to execute this initialize thread function only after initialize everything finishes. So a question says, assume we have n threads all set up to start executing run, and each thread receives a unique thread ID. In addition, that initialize center function executes before any threads get created, so it's safe to initialize the center. Then the question asks, using that single center sem, enforce the synchronization constraints specified in the comments. You may add code directly above in C or pseudocode. Be sure to give the center an initial value. Try to make a solution that supports any number of threads. Assume that thread 0 always exists. And for a maximum of 7 points, you can use that total threads in your solution and assume it's the number of threads executing the run function. So using a center how would I enforce those conditions? So I will give you a few minutes to think about that. Okay, where should I start? Yeah.
Like, I guess the starting point was just like figure out what the initial value you give to your semaphores.
Yeah, you could start with the initial value. So what do you want the initial value to be?
Guess 1.
Guess 1. So sometimes thinking about the initial value is usually the second step. First step, it's usually easier to figure out where to put the weight. So in this case, what should be weighting? Yeah, the other threads that are not 0. So if I have this if condition, and then let's say I have an else, so I could put a sem weight in the else, and now I should probably think about that initial value. So if I want to prevent any thread that is not thread 0 from executing, then what should the initial value be? 0? Yeah, 0. So, oh no, sorry. So the initial value is 0. Actually, can I just erase it? Nope, okay. So the initial value is 0. So now in this case, if I am not thread 0, then I wait. In this case, what's going to happen? So thread 0 will execute initialize everything, and then break out of its if, and then do initialize thread, and then all the other threads are going to be waiting. So next, I should probably place my post. Where should I place a post? Yeah.
The first if statement, like if thread ID equals 0 after you initialize everything.
Yeah, after I initialize everything, right here. I can do a sem post. All right, is that all I need to do?
You should post after the semicolon else.
Yeah, post also here. Like that.
That could probably cause a lot. It's like two threads wait.
Two threads can wait on a semaphore.
Yeah,
So semaphores are, remember semaphores are atomic, so it'll decrement only if it can. So should be okay, right? So here, first we can argue what happens if we don't have this post. So if I have 8 threads, say, well, let's say all thread 1, thread 2, all the way up to thread 7 will be sitting here at the wait, and the only thread that could execute is thread 1 or thread 0. It would execute initialize everything and then post. So my semaphore value would change from a 0 to a 1, and then one of those threads will be able to successfully pass the wait because it can decrement it now from a 1 to a 0. And then if I just left it as it is right now, only thread 0 and then one random thread can go ahead and execute this initialized thread. The other 6 threads will be stuck. So that's why I had to add a sem post here. So if I add a sem post here, then what will happen is as soon as one thread of thread 1 all the way to 7 makes it past the wait, it will post to increment it back from a 0 to a 1, and then another thread will wake up and make it past the wait, and then it will post, then another one can execute, and then it will post another one, then another one. It's like that DJ Khaled song, is that the one? It's another one, yeah, all right. So if I didn't want to put a post there, if that was confusing, what is something else I could have done that would have made, the 7 threads make it through the wait? So what about if I just did had this post, but instead it was for 1 to num threads. So thread 0 after it's done just posts 7 times. That would have also worked. But that solution, well, that was this one. That was for a maximum of 7 points. So you got -2 if you wanted to use that.
Why is that?
So that essentially doesn't work with any number of threads. You have to essentially, anytime you update the number of threads, you have to recompile everything. The first solution with just a post after, it doesn't matter how many threads, it'll wake them all up. All right, any questions about that one? All right, part 2. All right, so consider the following solution without semaphores. So we have a run, then we have if thread ID is 0, initialize everything. Otherwise, instead of a semaphore or anything, we just have a good old-fashioned yield. So now the question says, assume that we have cooperative user threads, aka like lab 4 for you. is this a valid solution that actually adheres to those conditions? Explain why or why not. Yeah.
If like not like the first thread, like for example, if like thread one runs first and then it'll go to L7 and walk yield directly without initializing everything. I thought we want to initialize everything first.
Yeah, we want to initialize everything first before an initialized thread comes in. So yeah, the only condition is here is that initialize everything should execute before any thread runs initialize thread.
Like, are the threads not being like waken up somehow?
So assuming this is like your lab 4, if you yield, what happens? Goes to the next one. Yeah, it goes to the next one. There's like a FIFO queue you had, right? So it just goes to the back. So assuming you had a FIFO queue, would this work? So initially all threads are somewhere in the queue in any order. And then you get a turn. And then if you get a turn, you just yield, so you go to the back of the line. So eventually, as long as you go to the back of the line, eventually thread 0 will come up before any other thread wakes up again. And in that case, thread 0 would call initialize everything, and then the others would call initialize thread after they wake up, or after they get re-queued again. Yep.
Like I thought like when you call thread yield and then you just like for example thread 1 called thread yield and it goes to the next one, goes to the next one until we get like thread 0 and it will initialize everything. But how do you reach to like the and then how do you reach with the initialized thread?
So whenever they get re-queued, they'll resume back from the yield, right? So they'll context switch back and they'll resume from the yield, and then they'll just fall and then they'll just fall through and then execute initialize thread. So seems like a valid solution, right? If you had lab 4. So assuming, like this question says, assuming you have a FIFO queue and it's essentially your lab 4. So for you, it's lab 4, it was lab 3 before. So everyone would give up their turn, no other thread would get re-queued ahead of thread 0, and then initialize everything would run first. Next part says, assume we have cooperative kernel threads now, running on multiple cores. Does the solution work now? So let's yeah.
Based on the previous one, if it's running concurrently,
Yeah.
it works, but then for kernel thread, because it runs on multiple cores, it would be running in parallel, so it wouldn't work.
Yeah, so if they're kernel threads, they could run in parallel, and it could even be the situation where thread yield doesn't even do anything. So say you had, let's just start off with core 0, core 1, and core 2. Say this was executing thread 0, this was executing thread 1, this was executing thread 2. Say we were down to the atom timescale or something like that, and core 2 executed, and thread 2 executed, so it would go to this yield, and well, since the kernel decides scheduling decisions, thread 2 could yield, and it could be like, oh, well, that core is not doing anything else anyways, so just continue executing it. Don't worry about it. And then thread 2 would go ahead and then just call initialize thread, and it would be broken. And, well, they're running in parallel, so you don't know what's going to happen. And because they're kernel threads, they can be scheduled independently. You don't know what the scheduling algorithm is. So even if it couldn't run in parallel, this would still not be a solution because a real kernel can just ignore your yield. It's just a suggestion. So it ultimately decides the scheduling. So question says, no, this doesn't work since they're kernel threads. They might also run in parallel, so you can't ensure any kind of order. All right, any questions about that? All right, what do we want to do next? So what are our choices? So choices are one of those topics or one of those topics and we look at a different exam. File systems? All right, that is a good choice. So file systems. For the following questions, assume your file system has a block size of 4096. Each pointer to a block is 4 bytes, and inodes are 128 bytes each. So first question says, what is the minimum amount of space in bytes you need in a file system like ext2, aka your lab 6, to store 1,000 files? Assume that each file is 96 bytes in size. Include the size of the inodes in your calculation. You may skip the final calculation if you don't have a calculator. So each file needs an inode. So each file needs 128 bytes for an inode. And then even though a file only consumes 96 bytes, it still gets an entire block, right? So since it gets an entire block and only one block, then it would need this many bytes per file. So we need 128 plus 4096, which is what, 4,224 times 1,000 files. So our final answer is that number that I'm not going to try and say. So questions about the first part? All right, second part says, for the previous question, how many bytes are lost due to internal fragmentation? You may say 0 if that's the case. Yep.
It'd be like 4096 minus 96 for each file. It's like 1,000 times that. Or yeah, 1,000 times.
Yeah, 4,096 minus 96, so that's per file, and then times 1,000. So that should be 4,000 times 1,000, which would be 4 million. All right, so questions about that one? Yep.
Well, we get full marks if we just write out like 4,096 minus 96 times 1,000.
Yep. Yeah, full marks if you write down the right thing. So for this next question, why might copying a directory containing a single large file be faster than copying a directory with many small files, even if the total size of the small files is less than the size of the large file? And my inspiration behind this was, well, I was copying files on my computer, and then it got to a bunch of small files, and then you know the Windows progress, it just went, and then it's like, oh, wait, the class should be able to explain this now. So I wrote a question. So why would that be the case? Yep.
So like, I think when you're copying like large files, all the system really needs to do is just copy the inode without actually like making a copy of the data that's inside.
It would still need to, yeah, you still need to make a copy of the data, like actual copying files. But you're on the right track. So for a single large file, it's one inode, right? And then all of its data would be in a bunch of IO blocks that are full, essentially, right? They would all be full except for the last one. So like if you have a single large file, it would probably look like, inode, and then that one inode, if we just had its blocks and didn't look at the structure, it would be pointing to like block 0 all the way up to, I don't know, block, what's large? Block 1 million, I don't know. Maybe that's too large. Let's say 10,000. Block 990. Block 9,999. So that's what a single large file would look like, right? So block 0 to block 9,998 would all be full, and this one, might have a little bit of internal fragmentation at the end, but its total internal fragmentation is going to be negligible. If there were a bunch of small files, well, for each small file, it would be an inode to a block, and this block could only have, I don't know, like a few bytes in it. So like 10 bytes, 100 bytes, whatever. But the file system still has to read the entire block. It can't just read part of a block in. So if we had a bunch of small files, say we had a lot of small files, so say we had, wow, that's not a good brace. So say we had 10,000 of these. So if we had 10,000 of them, we have to read the same number of blocks as that large file, but the contents of it, this could only be a few bytes. So this could be like 10 bytes. And I'd have to read the same number of blocks for way less data. I'm only copying 10 bytes a block that's actually useful. And for each of those, I also have to copy an inode. So most of my copying is going to be copying inodes and just accessing empty blocks all the time. And usually when Windows shows you file copying process, it only cares about the contents. And the size of the inode outweighs the contents even. And that doesn't even count. Yeah?
Doesn't the inode have the data for how big the actual file it's pointing to is?
Yeah.
So why does it still read the whole thing? Can't it know when it's read the end of the file according to the size and then just not read the rest?
Yeah, so the inode has a size on it that knows what's valid, but whenever you're reading from a disk, you can only read blocks at a time. Doesn't matter, right? With the SSD stuff, you can only read blocks or pages at a time. So even though that it only has a few bytes valid, given by the size, you still have to read the whole thing in. You wouldn't have to copy all of it, but you still have to read it in from disk. So that is also why once you hit small files, performance goes down because it only keeps track of copying the contents. Hey, the inodes could be bigger than the contents and they're not even counted. Yep.
So in the case of the small files that only have block 0, right?
Yep.
Would there be that optimization where in the inode itself it would have 12 blocks and one of them would just be on the inode?
So the question is, if it's a regular file and it's super, super small, can we have the same optimization as we had with the symlink, where we store the contents on the inode?
Yeah.
Yeah, so in that case, the reason that optimization does not exist for regular files is because, well, remember they're also mapped to virtual memory pages, so they have to correspond to something. If the contents were stored on the inode itself and you did that nmap magic thing, then suddenly if you tried to map its contents to the page, that page would also contain the whole inode and all the neighboring inodes. So then a process could just change inodes, which would not be good. So even for regular files, it does that so that it's on a page and it can map it to a page in memory and then carry on from there.
So the optimization is only for symlinks?
Yes, that optimization is only for symlinks because you can't really access its contents, like just the kernel reads it anyways, so it doesn't matter. And also symlinks generally don't change, and all symlinks are generally smaller than 60 bytes anyways. So that's why they do that optimization. All right. Oh, let's see. So next question. Assuming an inode has 12 direct blocks, and 1 indirect block, what is the maximum file size that can be supported? You may skip the final calculation if you don't have a calculator. So I will write the important things. So the block size was equal to 4096, which is 2 to the 12. And then the pointer size was equal to 4 bytes, or 2 to the 2. So if my inode has 12 direct blocks and 1 indirect blocks, what is the maximum file size in kilobytes that could be supported? So how many blocks could I point to with an inode that just has 12 direct pointers and 1 indirect? So let's start off with first. If I only had 12 direct pointers, how big could the file be?
12 times the block size.
Yeah, 12 times the block size. So in this case, it would be 12 times, they would be pointing to a block. So 12 times the block size, which if we want to just keep it in kilobytes, it would just be 12 times 4, or 48 kilobytes. Okay, what about if I just had a single indirect block? How big could the file be? So the first idea behind this is like with page tables. So it's like, how many pointers could I fit on an indirect block? Two to the 12 or, sorry?
2 to the 12 divided by pointer size?
Yeah, so 2 to the 12, so it's block size divided by pointer size is how many pointers I could fit on a single block, which would be 2 to the 10, right? The number of pointers per block. So if I only have a single indirect block, then I can point up to 2 to the 10 things. So I could point to 12 plus that 2 to the 10, which is equal to, this is 1024. So in total, I could point to 1036 blocks. And if each of them is 4 kilobytes, then that is the maximum size of the file. In that case, it would be, what is that, times 4. So that would be 4,144 kilobytes. All right, any questions about that one? Yeah.
Sorry, so it's like 2 to the 10 pointers points to that many blocks, plus there are 12 direct ones.
Yep.
So that's 1,036 blocks, and each block times 4 is because
Each block is 4 kilobytes. So this is aka 4 kilobytes. But if you just wrote it in bytes, probably fine.
if I answered like not in kilobytes, will it still be like fine?
Yeah, probably, I think it was in bold, so I think it was like a minor deduction if it wasn't in kilobytes. I forget.
It was like 1,036 times 4096,000 bytes, right?
Yeah, if you just did something, like as long as you knew what you were doing, so if you did like, even wrote 12 plus 2 to the 10 times 2 to the 12, all divided by 2 to the 10, that's fine. Yep.
So like, why don't we consider the fact that like a pointer can also point to like a block which has like pointers. So like we just like kind of like the multi-level page table.
So the multi-level page table, this says just one indirect block. So that, it kind of implies single indirect. Maybe I should have said single indirect. But the ones you're talking about, it would be explicitly like double indirect and then triple indirect. I guess this should have probably stated single. But if you just made up double or something for that, I guess I would have to give you full marks because I didn't, you could argue that one. Okay, is there more? Oh yeah, okay. So, let's get rid of this. No! Okay, so how many directories need to be accessed when attempting to read a file located at home user, uToronto, ECE, blah, 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 labs, grade.txt. Assume grade.txt is a regular file. So how many directories do I need to access to actually get to that file? And what are their names? Yeah.
Kind of just like the number of slashes, like the root directory,
Yes.
user one, uToronto, ECE 353 labs.
Yeah, so
5.
root, and then this, right? So that's 5. So, yay, 5. So this question is mostly so you knew that the root directory was an actual directory. The other answer I mostly got was like 4. So, next question. You think you should create a copy on write file system, but someone who hasn't taken this class says you don't need to because you can already do the same thing with hard links. Explain the differences between file 1 and file 2 being hard links to the same inode and the concept of copy on write. Can copy on write be achieved using hard links? Yeah.
So like a hard link, you can have 2 hard links to the same data.
Yeah.
But once one of them writes to the data or changes the data, it's changed for both of them. It doesn't create a separate copy. So if you have 2 copies, then they're both going to point to the same thing, and you can't have 2 separate actual copies. But I guess if you have like a system where you could check the amount of hard links to a data block, and then if it's more than one and you want to write to it, you could make a new data block, and that seems kind of impractical. I don't know.
Yeah. So basically, that probably would have been full marks. So if you just said that if you have 2 hard links to the same inode, well, if you change the file through one or the other, it changes them for both. They're not independent at that point, so you wouldn't get the same effect as copy on write. What you would want, because they share the same data, what you would want is to, oh, Jesus. What you would want, what are you, stop it. So what you would want is for 2 inodes to share the same blocks if they are the same, and then if one tries to modify it, then you create an independent copy of it. And you could do that if you want for the file system, so you could make like that copy command, essentially do copy on write instead of copying the contents. And there are file systems that do that, but they would have different inodes, and then internally the file system would have to keep track of the pages exactly like in memory. Yep.
So what's it called? The inode has the information for how many hard links are pointing to it, right?
Yep. Yep. Okay, I think that was it for file systems. All right, anything we want to do real quick in the last 6 minutes? Okay, that's a blank page. Let's see. Threads, we want to do threads as quick as we can? Sure, okay. So here's our program. So we declare a bunch of threads, we get a bunch of IDs, then in the main thread, we create, what in this case, we create 8 threads. So we create 8 threads, each with their own ID, and then we join them and we print a global sum. Global sum is this variable, and then there is another global variable called array. And then in each thread, well, it seems to start us off at a unique index that doesn't overlap with any other threads. So like thread 0 would get, I don't know, let's say indexes 0 to, 0 to 10, not including 10, and then the next thread would get like 10 to 20, and then the next thread would get 20 to 30, so on and so forth. So, real quick, is it necessary to protect access with the array variable? So is there a data race with this array variable here? So anyone off the top of their heads remember definition of a data race? Yep.
2 concurrent actions when at least one of them is right.
Yeah, possible for 2 concurrent actions at the same location or with the same variable, with at least one of them being a write. So even if they overlapped in what parts of the array they are accessing, if we have the array on the right hand there, is that a read or a write? It's just a read. So local sum is being written to in red, but array is just being read. So do we have a data race with array? No, because it's just being read. All right. Next question is, do we have a data race with local sum? Yes? No? Yeah, no, right? So local sum is a local variable in each thread. So each thread has its own independent stack. So therefore, there's no concurrent accesses to the same location because each thread gets its own unique location. So no data race with local sum. Is there a data race with global sum? Yes. Why?
If they are running concurrently, but they all act as a local sum.
Yeah, so here, this is a write, and they all are concurrently writing, and well, guess what? They're also reading and writing. So all of them have access to the same location. It's the same variable, so all of them will be reading and writing. There's no protection. They could all be running concurrently, and therefore we have a data race with global sum. So what is an easy way to fix this? Lock and unlock, so create a mutex. And then where would I lock? Just before the global sum, because I would want to make my critical section as small as possible, and then I need an unlock right after, right? Boom, fixed. I think that was all the questions. Oh, then last one, really, really quick. If we change all the threads to detached threads, is that a problem? So now I detach them, and if they're detached, then I can no longer join them, so I don't have this. So is that a problem? Yeah. So it's not a problem?
It's kind of like you just go to return error.
Yeah, so in this case, it would be a problem because I probably care about the global sum. What could happen if I just attached everything is before all the other threads run, the main thread just prints the global sum. Global sum is 0, so it would print 0, and then return from main, which is the same as exit, and now the process is done. So could do that before anything runs, or it could, have one thread updated and not all of them. Recipe for disaster here, because we want each thread to be done before we print the global sum. So we need joinable threads in this case, or center fours or something like that. All right, so with that, remember, pulling for you.